So if you don't recall the change of base formula from back in the day, maybe Algebra 2, this is something that we can use to rewrite a logarithmic expression in another base. So the reason we care about this is because if we were dealing with log base 2 of x, for example, we don't know how to take the derivative of log base 2 of x yet, but if we use the change of base formula, we can just rewrite this. And you can memorize the change of base formula, but it's not so hard to derive it either. Let me just do a quick derivation here. If we have y equals log base 2 of x, then I know that 2 to the y equals x. And if I take the natural log of both sides of this equation, then I use properties of logs to pull that y out front, and I get y times the natural log of 2 equals the natural log of x, or y equals the natural log of x divided by the natural log of 2. So that's what this is showing us here anyway, is we can take the natural log of the argument in the numerator, and then we can take the natural log of the base in the denominator. So either way you want to think of it is the change of base formula, and when we write it like this, we realize, oh, well actually this 1 over the natural log of 2 is a coefficient. This is a constant. It's not a pretty constant, but it's a constant. And when we take the derivative, we get dy dx on the left side, and that constant is a scalar factor that sticks around, and we're left with 1 over x for the derivative of the natural log of x, which is something that we knew, right? So using those log base e problems, we can do these. So in general, you can imagine that base a doesn't really matter whatever the value is. It has to be positive, and it has to be not equal to 1. But in general, it's going to work the same way each and every single time. So log base a of x differentiates to 1 over the natural log of a times 1 over x. Or more generally, if our argument is some variable expression of x, we'll call it u, then we take u prime over u, which is exactly what we're used to seeing. We just have this extra factor of 1 over the natural log of the base. In fact, think about what 1 over the natural log of e is. We know that the natural log of e is 1, so that's just going to equal 1. So we can still use this rule even if the base is e, which we don't really think about because it doesn't matter, but we can if we want to. So with these problems right here, you can imagine that it's going to work pretty much the same way as any other natural log problem. We just have to remember to multiply by the reciprocal of the natural log of the base. So for dy dx on this problem, we've got a product. So we'll go ahead and use the product rule. U prime v is 1 times the log base 5 of x plus uv prime. So u times 1 over the natural log of 5 times 1 over x. And those x's cancel out in that second term. So we've got log base 5 of x plus 1 over the natural log of 5. Now, when I look at this, I think that looks kind of weird because we have a log base 5 and a natural log in our answer. So I would probably write this as natural log of x over natural log of 5 using that change of base formula to rewrite this plus 1 over the natural log of 5. And of course, now we have a common denominator, so might as well go ahead and write this as your final answer. Another option is use the change of base formula at the beginning, and then we wouldn't have to probably have quite so many steps. So it's just another way to think of it. But I'm going to go ahead and use these formulas up here instead, because why not? So anyway, we've got this next problem. F prime of x is going to be, well, we've got the log base 3, so we better divide by the natural log of 3. And then we've got, this should look familiar. We're going to put the sine of x in the denominator. We're going to put the derivative of the sine of x in the numerator. And that's fine as your final answer, but we probably would simplify this to be the cotangent of x. That's all you've got to do. And then with this last one, don't forget that properties of logs is a thing. So we definitely want to rewrite this as the sum and difference of logarithmic expressions. So anything in the numerator, we're going to add, and anything in the denominator, we're going to subtract. So keep in mind, of course, that this is not a derivative step. This is not a calculus step at all. This is simply a property of logs step. So this is still g of x. We haven't done the derivative yet. So if we then take the derivative, we say, well, this is, well, the base is not written here, but we remember that that's the common log, so that means it's base 10. So 1 divided by the natural log of 10 times 1 over x. In fact, all of these are going to be base 10, so I'll just keep this factored out. Plus 1 over x plus 1, that's for this one, and then minus, we'll have 1/2, and then the x squared plus 1 goes in the denominator, but the 2x goes in the numerator. That's the derivative of the denominator. So that'll simplify. The rest of this won't, unless we want to find common denominators, which I don't feel like doing, but you're welcome to if you like. The 2's cancel out, and we're left with this as our final answer. Great. Going in reverse, well, let's use logarithmic differentiation. We know how to do that. We'll take the natural log of both sides. And if I take the natural log of 2 to the x, I can get x times the natural log of 2. Just pull that exponent out front. And then when we differentiate this, we get 1 over y times dy dx equals, well, don't think about the product rule here because natural log of 2 is just a constant that's being multiplied by x. So we'll go ahead and just say that this is natural log of 2, right? This is just like the derivative of 2x is 2. The derivative of natural log of 2 times x is natural log of 2. So dy dx equals natural log of 2 times y. But we know that y is the same thing as 2 to the x. So we're seeing a new formula here, just like the natural logs, except this time we're multiplying instead of dividing by the natural log of the base. Whoops, so it's not 2, is it? It's, in general, it's a. And then, just like with e to the x, a to the x is still going to be part of your answer. We just have this extra constant factor out here. And of course, if we want to incorporate the chain rule, nothing to it. We just have a to the u, and then u prime. And again, don't forget to multiply by the natural log of the base, if the base is not e. So yeah, these are going to work pretty much the same way. Product rule again, so dy dx u prime v is going to be 1 times 4 to the x plus uv prime. So u is x, v prime is going to be the natural log of 4 times 4 to the x. So that's an okay final answer, but as we are used to seeing, the exponential expression shows up everywhere, whether it's the original or the derivative. So factor that part out to make it a little cleaner answer, and we get 1 plus x times the natural log of 4. Same deal here. This time we've got a composition instead of a product, so we're using the chain rule. So derivative of 3 raised to the u is going to be natural log of 3 times 3 to the u. And don't forget the chain rule, so multiply that by 2x. Or if you prefer, 2 times the natural log of 3 times x times 3 raised to the x squared. And you can organize this however you feel fit. You might want to consider logarithmic differentiation on this one, or alternatively, quotient rule. I'll go ahead and do quotient rule. Why not? It's been a while since I've done quotient rule. So u prime v is going to be natural log of 10 times 10 to the x times x raised to the 1/2 minus uv prime, so 10 to the x times 1/2 x to the negative 1/2. And that's going to be all over v squared, which is going to be x. So I'll factor out a 10 to the x. I'll also factor out an x to the negative 1/2. And that's going to leave me with a natural log of 10 in the first factor, or the first term rather. Also an x, right, because x to the negative 1/2 times x to the 1 is going to give us x to the positive 1/2. Minus, and then this is gone. The 1/2 is still there, but the x to the negative 1/2 is gone. So that cleans up fairly nicely. And we can drop this down to the bottom. We'll get 10 to the x over x to the 3 halves times whatever's left, which is x times the natural log of 10 minus 1/2. And there are some other ways you can write that, but I think that's a fine way to write the answer. All right. On this one, if we're going to try to find the second derivative, well, I think we're going to run out of time before I finish this one on this particular video. We'll do it on the next one. Tune in next time.